Hi there. We are now going to go through our first case problem, which involves moving two stacked blocks. In the graphic on the left, the applied force is on the top block, labeled as block 1. In the graphic on the right, the applied force is on the bottom block, labeled as block 2. Both these blocks are resting on top of one another. The upper block has a lower mass than the lower block. We shall further assume that the coefficient of static friction between the blocks is given by μs. There are two parts to this question. The question in blue refers to the left graphic, whereas the question in red refers to the right graphic. And both have been circled with the relevant colors. So let us begin. For the left graphic, we apply a force on the upper block, and we want to determine the maximum force that can be applied so that these two blocks do not slip. We have to identify the action-reaction pairs of forces in this problem. So let us proceed. We begin by drawing the free body diagrams, sometimes called the force body diagrams. The upper block is colored green here, and we note that there is an acceleration on this block. Remember that acceleration is always associated with force. Let us denote this acceleration with the variable a. We observe a frictional force called F of s acting in the leftward direction, and that is due to the lower block holding the upper block back. There is also a normal force exerted by the lower block on the upper block and is labeled M. And there is also the weight of the upper block, which is given by M1 times G. And last but not least, do not forget the applied force F. For the lower block, colored orange, we have the following forces. The normal force N exerted by the upper green block on the orange block, the frictional force F of s, and note that it is acting in the opposite direction to the frictional force on the green block, as the frictional force on the orange block is due to the potential motion of the green block. There is also the weight of the orange block itself and is denoted by M2 times G. Lastly, we have the normal force exerted by the ground on the orange block, and that is given by the term Ng. As we desire to move both blocks, there is an acceleration on both the lower orange block and the upper green block, in which the acceleration is labeled as A. Now we can proceed to write down Newton's second law of motion, which is essentially a force balance equation in the x and y directions. There is no motion in the y direction, and there is only a common motion in the x direction for both blocks. Here we shall employ the standard vectors associated with the x and y axes, namely the vector I and the vector j. So for block 1, we have the applied force capital F minus the frictional force F of s, and this is equal to the mass of block 1 times the acceleration. In the j direction, the normal force exerted by the lower block balances the weight of the block, the result of which is the equation N equals to M1 times G. For the second block, the force balance equation in the I direction require that the frictional force balances the mass of block 2 times the acceleration A. In the j direction, the normal force due to the ground must balance the weights of both blocks. The acceleration is not given in the problem, and we are only given the pulling force on block 1, that is, capital F. Using the equations in the I direction, we have A equals F of S divided by M2 for block 2, and A equals capital F minus F of S divided by M1 for block 1. We proceed to equate both these terms for acceleration, and this allows us to express the frictional force F of S in terms of the masses of the two blocks and the applied force capital F. At this time, we would like to recall the concept of static friction, shown in green. First, the static friction is a force that keeps an object at rest. It must be overcome in order to start moving an object. And once this object is in motion, it will then begin to experience kinetic friction. If a small amount of force is applied to an object, the static friction has an equal magnitude in the opposite direction. If the force is increased, then the maximum static friction will be reached, and above this value, the object will move, or in this instance, slip. The static friction is given by the relevant coefficient multiplied by the normal force. The normal force must be from block 1 because the weight of block 1 is the source of friction between the two blocks. Please pause the video now if you are unsure of this, and please review the lecture notes. Okay, so let us continue. So the maximum static friction that will be reached is given by mu s times the weight of block 1. And using the relations we obtained in the previous slide, that is, the frictional force F of S is m2 divided by m1 plus m2 times the applied force capital F. We now want to find the applied force, since we now have the expression for the frictional force, and it is given as m1 plus m2 divided by m2 times the coefficient of static friction, mu s times the weight of block 1. There are more slides featuring the solution for the second question here, where the applied force is now acting on the lower block. The method of solution is the same as what we have just covered. So before proceeding, please make sure that you are thoroughly clear about the solution for this first part before proceeding. For the full solution to the second part of the problem, please refer to the slides. This concludes the presentation for this case problem. Thank you for your attention.